Okay, we've got a worked example for a differential equations problem here, and this is it's quite an interesting little problem because it doesn't actually involve just two variables like a lot of the differential equations that we tend to see at A level. This one's actually got four involved. So apart from T, we've got for this cube, we've got the volume, the surface area, and the linear length of one edge. So we have to do a little bit of conversion. And I think this helps to illustrate the idea that we're dealing with a dx, a small change in x, and so on, virtually as if they're parts of a ratio. So let's just have a look at in a little bit more detail. At time t seconds, the length of the side of a cube is x, length, surface area of the cube is s, and the volume is v. Well, we know that the volume therefore is x cubed, surface area is 6x squared, and we're told that the surface area of the cube is increasing at a constant rate of 8 square centimeters per second. So ds dt equals 8. So we've got a bit of a connection between all these different variables, as we can see. And it says show that dx dt equals k over x, where k is a constant to be found. All right, so what we haven't got is dx dt. We know the rate of change of the surface area, and we've got to translate that into the rate of change of this linear length. Okay, well, if we just write out dx dt, and what we're doing here is we're using the chain rule. So we're kind of, it's sort of chain rule in reverse, if you like, chain rule for calculus in reverse. So we're kind of expanding it out, putting these ds's in, and we're entitled to do this. So dx dt is actually the product of these two derivatives. So we can put the s's back in, and once we do that, it starts to make a bit more sense, doesn't it? Because well, this ds dt we're told is 8. That's the 8 in our numerator there. And this dx ds, well, dx ds, again, it's a sort of corollary of the chain rule. Dx ds is the inverse of ds dx, and we know what the ds dx is because we can just form this, the derivative of s here. So ds dx equals 12x, just using the power rule. So our expression here becomes 8 divided by 12x, or 2 over 3x. And therefore, we've shown what we've been asked, and k is equal to 2/3, constant to be found. Okay, so pretty straightforward. I've just done it more or less on, on one line here. And then second part B, dv dt, show that dv dt equals 2 times v to the power of 1/3. Okay, so the same thing. We write out dv dt, and now we know what dx dt is. So if we just do the expansion using the chain rule in reverse, then we can say dv dx times dx dt is equal to dv dt. Now dv dx, again, we know what this is. We can just form the derivative from this. So that's 3x squared. So we've got 3x squared times dx dt, which we know to be 2 over 3x, and that simplifies to 2x. But going back to this equation, we basically want to put this in terms of v. So so dv dt equals 2x is correct, but that's not what they're asking for. They're asking for dv dt in terms of v. So, but quite simply, x is v to the power of a third, cube root of v. So therefore, dv dt equals 2 from there times v to the power of a third. Okay, so again, just a couple of lines to do that. All right, so now it says given that v equals 8 when t equals 0, so they're giving us the boundary conditions, and this is kind of looks like we're going to be integrating to resolve for v and t. And in fact, it says solve the differential equation in part B and find the value of t when v equals this. Okay, so first things first, let's solve this differential equation. Right, well, just using our separation technique, then what we've got is dv over v cubed equals 2dt. Let's just put the integrals in and express this as a negative power. And I think therefore it becomes a bit easier to see that when we integrate that, we're going to get this expression here. Again, just using the power rule with our constant of integration there. Substituting our boundary condition values, v equals 8, t equals 0, and if you just work that through, that's going to give you c equals 6. So we can write this general solution here as v to the power of 2/3 equals 4 over 3 t plus 4. Okay, you might just want to pause and just check that for yourself, but that's basically what it works through to. And then the last part is find the value of t when v equals 16√2. Well, okay, well, this is pretty straightforward. All we're doing is substituting 16√2 in for v, so v to the power of 2/3 is going to be 8, and then we just apply 8 equals 4 over 3 t plus 4, and that works out to t equals 3. So so that's it. So yeah, so quite a nice example, but I do suggest if you get something like this, then start off with what you need to know in this example here, dx dt, and it'll probably become apparent how we actually use that to and form this expansion here. So I think that's that's sort of the way forward with this kind of problem. Okay, so hopefully that has helped you, and I'll see you next time.